Okay, good morning, everyone. Welcome to the last day of the Limit 2024 online camp. So today we have with us Bikram. He is a student at ISI Kolkata. He's currently doing his master's and he is going into his master's second year. He's mainly interested in probability, and today he'll be talking about flows and actions, so mainly networks and flows. So over to you, Bikram.
Thank you, Rishik, for the kind introduction. So, as my title suggests, I will talk about flows. Flows, as in means uh, flows on a graph or on a network. You probably you people have already seen this in some other form. So let's start. So, as the talk progresses, uh, the level might the graph of the level might look like this. First, actually, I will talk about the problem of table rounding, then matching. You probably have already seen this in the graph theory tutorial. Uh, and Then I will talk about the image segmentation now. So that is you have a photo and you want to remove the background of the photo. That kind of problem. And then uh, with all these three problems, that there's very elegant approach to do this, right? With flows and networks. I will define flows networks. Then I will talk about some algorithm from which you can solve all these problems. And then um, I will take some time to give some concluding remarks at this in this time. So let's start with the table rounding example. Probably the most simple one. I can motivate you from this. So suppose um, we have census data from say some to, 2011. Although these values are not exact, I have taken it from somewhere. Uh, so don't believe in these values. So we take age groups in the rows and language in the column, and we actually count how many, maybe crore, how in crore, that how many people speak these languages in different age groups. Now, the thing is that uh, this is okay. I mean, if when you collect census data or something like that, you need accurate things. But when you try to publish reports, maybe you are a reporter, maybe you want to try to publish report from this data, but these decimal values, uh, people usually don't put these decimal values. They usually put some approximate round figures. So so if we sum this up, that this many people speak Hindi, this many people speak Bengali, or this many people speak Tamil. uh, Also, we sum along the categories, along the different age groups. uh, then rounding all this may cause some errors, like if I try to blindly round all this, uh, maybe uh, if you the row sum might stay same, the column sum might be okay, but the total whatever the total is, this may get deviated, and the round may not be the this may not be the case. The round figure will come. So uh, what we want to do, instead of usual rounding, we'll round each of the entries and each of the these column sums uh, and row sums up or down. So we're taking the ceiling function or floor function of all these values, and we want to make sure that this rounding up or down, this remains consistent. So if you now now the thing is that, okay, maybe for this I have one solution, that you round down this, round up this, or round down this, or and so on. Okay, the sum remains consistent actually. Uh, and say we call it a feasible matrix rounding, you can see it as a matrix and we call it feasible matrix rounding. But the thing is, in general, this may not be the case. So one question is that how to find such a matrix rounding? Maybe we showed one instance, that's okay. But in general, if we want to do this, let's say 3 by 3, but if we want to do this for say for say some thousand by some million uh, matrix, now how can we do this? We want to tell the computer to do this. Uh, so we want to find one algorithm, and moreover, does it even exist? If you oftentimes in mathematics, um, if before getting something we actually talk about existence, under which if it doesn't exist, under which condition it might exist, because we can see one instance that's so fine. uh, so this kind of problem I will talk about this kind of problem today. Now the thing is that, as I said earlier, usual rounding can fail. Suppose you have all these point 0.4 values, but the sums are 0.8s. But if you just blindly round it, the zero point 0.4 goes to 0 and so on. The 0.8 goes to 1, 1.6 goes to 2. This thing becomes very abstract. This doesn't even make sense. So, whenever we mean rounding, we just mean rounding up or down the ceiling or floor. Are people fine with this? Maybe you can. Someone raise hand. Do you have any question? You can ask me. Yeah, it's really important. I think it should have been 4. And they four. If you make it 4, actually it won't fail. Just a minute. In this case, it won't fail, but just say if make it 4, then say it 12, you make it 16.
17.
It is the 17. Sorry, never 17. Right. Will fail actually. It is not the usual rounding. Even this 41, if it becomes 42, then yeah, the usual running won't come. Yeah, thank you. So, but of course, because before formulating the problem, we need to rigorously understand what is there in mathematics. This is very important step, the formulating rigorously the problem. So, we take the table to be a matrix, let's say m by n matrix, and entries are dij, and I denote ri to be the row sum, cj to be the column sums, just as in these colors, as you can see. And I want to denote the integral values. I want to find the integral values of these entries. Integral values are in the round up or rounded down values. Say I denote them by bar, and so this uh, I want to find this. So how to find? Okay, we have algorithm or something like that. So this is one problem I will talk about. The next is matching or marriage. Probably you have already seen this in graph theory tutorial. So suppose you have n men, say they are n equal to 5, and n women. Each man have some preferences, and yeah, we denote preferences to be symmetric. We assume preferences symmetric. If one prefers two, then two, sorry, two dash, then two dash prefers one, like that. And we want to find a matching. So yeah, just one thing. Yeah, we want to find one matching. That matching here, uh, matching means just according to these preferences, can we find some matches among these men and women? So, to be defined rigorously, matching is just a subset of edges M such that any two edges in M have no vertex in common. Of course, we assume that uh, someone, if someone marries, say one dash marries one, uh, he can't marry to three. Of course, we assume these things. That's why say this is a matching. And if may not be perfect, there can be some people who remain unmatched. We want to find the maximum possible. Now, um, again, we want to to understand further, we first formulate it rigorously. Say we have bipartite graph. Have you seen this in the Devansh's graph theory tutorial, bipartite graph and everything? Maybe you can write it in the chat. I will see. So bipartite graph means you can decompose the vertex set into two disjoint subsets such that uh, among the vertices of A there is no edge, and same for B, and the only edges are between A and B. Yeah, that's what bipartite graph mean. And I want to find a matching, and may not be perfect, but maximum cardinality one. Now, for you, I would like to give you one exercise that cardinality of matching is at most half of the number of edges. Now, one thing is this equality. When this equality holds, we call it perfect matching. That uh, every other vertex is matched to someone. Now, in this case, actually, we do have a matching. One is matched to one dash, two is matched to two dash, three is matched to four dash, three dash matched to five, and four is matched to five dash. But one thing you see, and this is perfect matching actually. Every vertex in this set match to in this. Now, suppose I remove this edge. Still, yeah. Suppose I remove this edge, and I can't do this. But uh, yeah, now the thing becomes that this is a matching. That's okay, but um, it is not perfect. This is not matched to this, and you can show that there is no perfect matching here. Probably Devansh has stated this theorem, false marriage theorem. False marriage. That for this bipartite graph, uh, M is perfect if and only if, characterization actually, if and only if the neighbors of, say, any set of vertices, cardinality of the neighbors of any set of vertices has to be for all subsets in A. So yeah, you can try to find one counterexample where it actually violates. And yeah, Now again, how to find maximum matching. Again, I will come to this later. Uh, we have discussed two problems: the matrix sounding and this matching. Next, uh, next is assignment problem. This is somewhat uh, similar to matching, but uh, it's a weighted matching actually. It's a bit different. So say you have some students, some projects, and every student have some preferences. These projects you are let's say student one to prefers uh, physics more than biology or and then math. So he chooses project according to this, and uh, these values actually denote preferences. So the higher number it is, the more preference the student gives. So he, now yeah, this is one sided, unlike previous one, and we put a preference score on the edges, and we want to find what is the maximum preference maximum preference score uh, matching possible here. So again, we want to match this type of this kind of try to find this kind of edge sets. How to and uh, now the thing is, what we do, we take negative of this preference score. We call them cost, and just to make everything positive, we just add say maximum of this preference score, so that everything is positive. And we want to find, yeah, the cost is basically a function from edges to positive real numbers. So that's why we define like this: negative preference and plus the maximum successful, and we want to find a matching which actually minimizes the costs. So we have to find a minimum cost perfect matching. Say, yeah, perfect matching will come because everything is connected to everything else, and we might put zero if someone don't have any preference. So if even if there is no edge, we can put zero and talk about this. So the problem is that I want to minimize this sum actually. So here it actually exists. Okay. 3 plus 5 plus 4. So this, and this. You can check among the matchings here. This is minimum. But again, this just 3 by 3 problem. If if the size become large, let's say some million, among some million students, you want to put among some million workers, say, uh, you want to assign the workers some projects. How can you do that? So again, you want to find something algorithmic. How even if first of all, if it exists, whether it exists or not, and then you want to tell the computer to find like this. Yeah. Again, this is the second problem. Third problem, sorry. Fourth is image segmentation. So suppose you have an image and you want to segment different parts of the image. So foreground and middle, say, and background. How can you do that? This is, I mean, these two advanced. For now, we'll only talk about foreground and background. Uh, so and to divide the image into some coherent regions. If you know the term coherent, that means the regions that are consistent actually. And this is one of the central problem in solving. Maybe when you take Adobe Photoshop or maybe Google Photos. There, yeah, you can easily do this. Actually. Now, initially, this problem was studied using this flows and networks. So, this is a very simple. There are many actually. There is many progress in this problem, but initially, when people started studying this, they did like this. So what people do, they label each of the pixel of the image. So you can divide the image into a very various different pixels, the RGB values, and yeah, and belonging to foreground and background. You have vertex set as the all the pixels, and edge set will be the pair of neighboring pixels. And you define you actually define some values according to the likelihood that some pixel is in the foreground or background. So AI be the likelihood that pixel are in the foreground, and BI with the likelihood that pixel are in the background. And not only that, there might be some mistakes. So you take a separation penalty, PIJ. Everything is non-negative, so that our life become easy. And penalty that the separation penalty is for labeling one of the I and J as foreground and other as background. So uh, if if you mistaken if you by mistake label a foreground pixel as a lower value and a lower higher value in BIs, then there can be higher penalties like this. So what do you want to find? We want to find I mean, first of all, of course, we need accuracy. So if AI greater than much greater than BI in isolation, we prefer label I in the foreground. And smoothness. If many neighbors of I are labeled foreground, of course, we should include, um, say, you have nine actually, yeah, nine, many for each pixel. Sorry, for each pixel you have eight neighbors. Say they were almost seven or eight are in the foreground. Then of course it takes middle to be in the foreground. So that is what smoothness. And the main problem is, and to find a partition of the subsets of the vertices, um, so that I can maximize this. This is the sum in the foreground values, sum in the background values, and this is the penalty. This is basically um, this A intersection IJ means I. So one of the I and J belongs to A, and other one belongs to B. So so yeah. Sorry, someone said something. Okay. Uh, so yeah, these are the four problems that we'll talk about today. First of all, as my title suggests, uh, talk about flows on networks. So first of all, what is a network? Maybe a computer network. Of course, there are various different types. Maybe each computer is connected to a server and they communicate from there, or maybe each computer connected like this in a circular fashion, or as bus. We say local area network, like many other networks. So this is one example. The computer network is one example. Maybe if you have attended Professor Rajesh Shubhasra's talk, you may have uh, seen some of the examples. But for us, we will not deal with those. We will deal with this kind of network. Say, I have these are railway junctions, all these nodes, and The edges, the weight on the edges, that denotes the how many kilometers do you need to travel to go from this node to this node, like that. So there people mainly study maximum flow problem. So there might be rail crash somewhere if some if more and more number of rail trains are going there. So we want to detect if there can be any. So for that, they study this kind of problems. Or network might mean this, probably you have already seen this in Professor Rajat's talk, the Facebook network. So each node or each person, each account, and uh, two account two between two nodes there is a edge. If those two accounts are friends of each other, mutual friends, are mutual friends. So there is another sort of network. Or if you ask the AI nowadays, you have all these large language models. Ask DeepSeek, define a network. It actually gave me the definition of computer networks. Yeah. Uh, so in general point of view, maybe in general culture, maybe this is the one that people uh, talk about. But we'll talk about this kind of network actually, where we have various kinds of nodes, and between the nodes, they are directed, of course. These edges are directed. Uh, weights. Yeah. Okay. So we'll talk about flow networks. So this is basically an abstracted version of say, uh, network that I mean abstracted version of network that we study. Say so. What is that? Basically, graph. Not only graph, it is a directed graph. So each of the edges are directed, and there are no parallel edges. So this kind of thing is not allowed. And we have two distinguished vertices, a source and a sink, S and T, this and that. And for each edge, we have a capacity function. And uh, this is just definition of the network. And yeah, we have this capacity function. Of course, these are non-negative, we will assume. And maybe you can think of it like if you have studied physics, so you have say 200 volt here, 0 volt here, and this capacity is actually the inverse of the resistance, say, or yes, sorry, not inverse of the V by R, the V by R, that one. So how much current can flow from each of the edges? That's what this denotes. You can think like that, or maybe you can think like uh, uh, and to transport your raw materials from uh, some place, from say coal mine to your factory, where you have road network like this. These edges denote the road networks, and now how much you can take from one place to another. That this weights may denote that also. So these are just examples. Now, uh, and one thing is cut. Cut means just cut like this. Maybe I can draw. Yeah. like this. So cut means basically we separate the network into two distinct parts to actually partition the network, so that in one part there is a source and in other part the sink is there. Just this. So we call is, sorry, yeah, we call stick cut is a partition AB. So this part is A, this part is B, uh, and such that S should be belong to one part and T should belong to other part. Generally, can you explain the penalty thing once more? Oh, sorry, I missed it. Yes, sir, please, there was a talk on this. Oh, I see. Nice, nice. So, Lego is familiar with this, and I will not cover all this definition. I will directly go into that. Yeah, I will explain the penalty part. Maybe when I will come back, I will talk about the penalty. Is basically, so you put a value for, you put one value for the so for each pixel you put one value for the foreground or one value for the background. Now, if you by mistake assign more value for the foreground than the background, then we'll take more penalty in the account in that case. That's what I mean by penalty. I will talk about it later as well. Don't worry. So yeah, and second thing is capacity. Capacity between these partitions. I just take all these edges that are coming out from one side, and I sum those capacities. So say for example, like if you take A to be only this S, B to be of the rest of the network, and capacity becomes sum of all this capacity of this edges. Here in this case it is 30, or maybe this. Now, one of the central problem is finding the minimum capacity because, yeah, I will come to this also. Uh, so I want to find a cut such that its capacity is minimum. So that sort of gives you a bottleneck. How much, at most, how much can you take a flow from there? You can look at all these examples. So, another thing is flow that we call a stiff flow is a function on the edges such that the restriction is that it is between 0 to the capacity, and the upper bound should be the capacity. And for each vertex, uh, excluding S and T, those source and sinks, um, the Kirchhoff's law should be satisfied. Flow conservation should be satisfied. Whatever in one vertex, whatever you flow in, the same value should flow out. Maybe you can think of it like the electrical network, and the Kirchhoff's law, yeah, the Kirchhoff's law from the electrical network. And I call the value of the flow. So there might be many different flows. We have so for electrical networks. Yeah, no, that's fine. Yeah, so the flow has only lower bound zero and upper bound capacity. So you can take the zero flow is also a flow every for every e f of e is zero. So that will also be a flow. So for every flow, I define the value of the flow. That is basically uh, the sum of the flows that comes out of the sink source. So here I put 400. So the total value of the flow is 4. Or maybe if you put something more, 10, 3, 11, value becomes 24. And Again, another thing is the maximum flow problem. How much maximum flow you can actually push from the source that all gets sucked up in the sink. So here the maximum becomes actually 28. And yeah, so we'll talk about this as well. And there is very intricate relation between this maximum flow value and the minimum cut. So I have so one observation is the this lemma that for any flow and for any cut, it will be the net flow that you send across the cut equal to the amount of flow that leaves our source. So that means this is basically v value of f defined earlier, and this is basically the net flow across the cut. So I sum along the edges uh, going out of it or coming into minus into a, yeah, minus coming into a. This should be say. So this is now if you just you can take trivially this, although that is our definition. Then yeah, you can see the value to be 24 and 350. Or if you take this, yes, sorry,
I'm very sorry. Can you
continue.
go up with it because I missed it?
Yeah, sure, sure.
Yeah, like what just a little bit more. Like what is
One thing, there is a mistake at all these colors. This 15 should be in black and 11 should be in red. So yeah, and yeah.
wait, sorry, I
Sorry
missed
about
the
that.
what is the line with the amount of flow leaving us?
Oh, this one. Yeah. So if you take a partition, say of this network, the amount of flow that you sent across this partition is same as the value. Whatever the amount of flow you sent across that any partition actually. Take any partition, maybe this. You can say the flow value should be same.
Ah,
And this
okay.
remain that is the flow value actually. So yeah, you can look at all these different examples on this network. I will leave it to you. I will share, when I share the note, you can see this. So yeah, the proof of the lemma value basically the definition of this. Take some of the flows along the edges coming out of the source, and I add 0. So this is basically flow conservation. E going out of so any vertex V and minus E coming into any vertex V. So it's basically 0, and I take this sum uh, all over the cut A, excluding the source. Then just by the simple observation, you can not the simple sorry. Just you can include this s here. This become this because there is no incoming edge inside s inside the source. This is anyway 0 when v equal to s. So uh, taking this won't harm us, and you can just split it and see. So you can check. And yeah, the next observation is uh, uh, grid duality. So suppose you have any flow f and any cut again, then the value of the flow is always bounded by the capacity of the cut. You, so that's why we talk about the minimum cut and maximum flow, and we need to see if equality achieves or not or something like that. This always happens. So so suppose in this case here the cut capacity is 30. So maximum flow you can push is less than equal to 30 always. proof is fairly simple. You just use the previous lemma, and just because these are positive, you can ignore. You take less than equal to, and because flows are bounded by capacities, again take one another. You can get another inequality, and this is the capacity of. I hope these are clear. If any question, you can let me know. And one thing is optimality. As I talked about, uh, if at all there is an equality between these two, for some flow or for some cut, then if if at all this happens, we call F to be the max flow, and that partition of the network, that cut, to be the main cut. I will only use this terminology from now on. I, I will go into another terminology. So now my goal is optimization. So I want to find max flow or min cut. So maybe in this graphs in this network, you can see along this cut, the capacity is 28, and there is a flow that has value 20. So here actually the flow achieves its maximum value, and the cut actually there is a cut that actually achieves this minimum value. Let's see now how to find. So one of the strategy, the algorithms probably you see is the greedy strategy. I optimize at each step. I optimize. So here, what I do, I start with zero flow. So uh, every edge I put zero. So we have capacity. Say for this is 20, 10. Here it's 30. Here it's 10. I'll start with a zero flow, and then I will just add some flow values. I say. So here the flow is zero, and next what I do, I find an ST path from S to T a path such that this holds the strict inequality, not equality, and I augment some flow. So whatever the if, minimum is here, whatever minimum is possible here along this path, the minimum is 20. I send 20 there. So now value becomes 20 plus 0, that is 24. And I repeat this until I get stuck. And one can see that uh, yeah, one can see that uh, after this, I mean, you can't do anything much. This is this is the place where you get stuck for this network. But the thing is, the optimal flow value here is actually different. It is 30. So you send 20 across it across this edge and 10 across this edge. Then you can split this 20 into 10 and 10. Then combining this 10 and 10, you can send 20. So this kind of strategy actually doesn't give you any solution. So local, as any, if you have ever done greedy algorithms, you will always hear this statement: local optimality doesn't necessarily imply the global optimality. How much time I have? Uh, so yeah, greedy fails. And the next is that if greedy fails, so what kind of algorithm? We have an algorithm called fold filters algorithm. I will not go into the detail. The thing is, this also starts from some zero, and see how much, yeah, that uh, it takes a path, ST path, and takes minimum of the capacity in the path, what minimum capacity H, and then push that amount of flow through the source, through that path. Say I have minimum this 8, I push 8 here, and I just rewrite this network like this. Low value 8 now. And one thing, this actually helps in computer, when you record this in computer, when you tell this algorithm to the computer, there is something called residual network. So whatever you actually sent in your previous one, you actually take the edge back, and you see uh, uh, whatever remains you put on the edge. So here we have sent 8, so we sent 8 back, and put 10 minus 8, 2 here, and yeah, like this. I have 8. Here is and we can't uh, put any forward edge here because it is 0 anyway. But we still have two remains here. Now the thing is, this actually helps because you can see that you can still see how that it can push how much from the source. So next you can take this path, push 2, and you can go on like this. And you repeat this task actually. Repeat this task unless actually you, so in the residual graph actually, whatever you can push through the residual graph, and you repeat this task unless you get stuck. Get stuck means this kind of situation. So here you, in the residual network, um, you can send one from here, but from from the vertex 3 you can't send anything from anything to anywhere. So yeah, and yeah, again, you can't send s from the source from s to t anything, you can't send anything. So yeah, so get stuck means this, unless you can't send anything, you repeat the process. But you repeat the process on the residual network. Now, it's not the original network. It's the residual one where you have a you back edges uh, whatever flow you had in the previous graph. So here you can see the cut capacity, that is 19, and the flow value is 19. Yeah, it is a optimal one. You have reached cut. So I have written down the algorithm for you. So you can maybe later check it out. Check it out. So there are, first find the augmented path, find the bottleneck edge, even minimum capacity edge is there. For each edge, you assign you actually take plus b or minus b accordingly on the residual graph. And you return the flow. And the Fulkerson graph takes this graph, uh, source and sink, and the capacity. For each edge, start with the zero flow. You construct the residual graph, and while there is augmenting path, you augment along this FC and P, F to this FC and P, and you update the residual network, and you return the flow at it. Now, for finite networks, this actually terminates. So, this actually terminates. Let's see some of the consequences. So, call it augmenting path theorem. If flow is maximum if and only if there exists no augmenting path. So you can see the residual network, you can't find any augmenting path here. So if you try to find, if you can at most try to go here. After that, you get stuck. But before that, you had augmented parts like this happens. Is the idea clear? I skipped many details actually. Maybe you can write in our chat. Alright. Fort Wilkerson showed in 1946, 1956 that that equality actually we can achieve through their algorithm. Now let's go back to our assignment problem. That we had the student and project the students set of students and the project and their preferences according to the preference course. But what we do, we take cost. This cost to be the negative of the preference score plus the maximum of whatever the preference score was. This become negative. Now you can just say that this cost is basically capacity, and you can draw this capacity network. And of course, yeah, before that you put the source and sink, and you put zero cost along those edges from the source to the sink, and you consider this network. So whatever your task is, you find the minimum cut. That will suffice. That will give you just use the algorithm that I described. This will give you the optimal project student project pairing. Now, if I go back to the marriage problems. May- Actually, actually, you can uh, take a you can yeah right. Then just take some take this preference course to be 1 1 1 1 1 and consider the marriage problem. Then one or two maybe. And then your actual because you can take constant here. This whole problem will convert into the marriage problem. Yeah, uh, basically we do. So we create a directed graph. I had the set of men, and I put sources and source and sink, and I assign unit capacity to each of the edges. It is 1 1 1 1 1 here as well, and I direct just a minute. Just a minute. Sorry for the inconvenience. Yeah. So yeah. So what you convert this match problem into the flow problem. Uh, I I direct these edges actually. I direct all these edges. You can see that if you do the reverse as well. Consider this to be source, consider this to be thing, and you take the reverse direction. The answer will be the same, or maybe different, but you can find one perfect matching, one perfect or maybe maximum matching. So near our goal is just become finding maximum flux, and you can try it out. The flow value would be 5 because whatever comes out is total is 5. Can be 5, yeah. And this or this should be this would be your flow your paths of the flow. Yeah, here actually the augmented you need to find the path as well. So with this you can find you can find a perfect matching, just or maybe maximum matching. Maybe you had this vertex, this yeah, this one removed, then can't put this here flow value becomes 4. So you didn't have this. If you have a maximum matching, perfect. But yeah, you can do this using flows as well. You can also prove the Hall's match from theorem from. I can give you one exercise. So exercise. Hall's match from network flow solution. So I have out of time, or I have really less time actually. So that is what. Maybe I can take 2 more minutes, 2 or 3 more minutes. Is that fine?
Yeah, sure.
Yeah, yeah. So we have, if I now, yeah. So these are the two problems that can be solved using these flows and networks. Now I'll come to the table run. So if we assume that all these capacities are integers between say 1 and some maximum value, the capacity is say bounded, they are bounded. Then you can see from the algorithm, whatever we perform, that every flow value and every residual capacity remains the integer. You can keep them as integers throughout the algorithm. Just it's an observation. If you uh, try to work out the algorithm and by hand, that you can see this. You can also prove this. I won't go into the details. I don't have much time. Then this actually implies a very important result, that as capacities are integer, then there exists a maximum flow f for which every flow value is an integer. So that's what the uh, or that's what will give what table rounding problem. But the solution to the table rounding problem. But the thing is, here I have a lower bound as well. If I maybe I had this table, this 1, 2, 3 say, yeah, see these 1, 2, 3 say these are rows, the age group, and these 1 dash 2 dash 3 dash these are columns, the languages. And what I do, I put an edge. If I put an edge and weight like this. So weight means, sorry, weight is capacity and a lower bound. So uh, from 1 to 1 dash 1, sorry, 1 to 1 dash, I have lower bound 3 and upper bound 4, and so on. And play around it. And okay. And yeah, uh, from the source to 1, that basically this will mean the row sum. Oh, sorry, the first column sum, second column sum, third column sum. First row sum, second row sum, third row sum. And this, okay, not this one is not for here. But yeah, so we had algorithm for when we have capacity, not the lower bounds. Maybe you can actually you can modify this uh, to get uh, to get result for the lower bounds as well. So we have lower bound and upper bound on the flow. So now what you talk about circulation. So what is circulation? Just like before, I have directed graph, H capacities, and circulation is a function. Just like the before, I had a lower bound and upper bound. Uh, yeah, maybe you can take some lower bound as well here. Won't be a problem. And at each edge, now I am not excluding the source and sink and doing it for each edge. Each edge, whatever goes in, uh, sorry, for yeah, for each edge, whatever uh, sorry, for not for each, not for each vertices, whatever goes in, that comes out. So if you can see that if you in the flow network, maybe, yeah, in a flow network, if you join the sink and the source, it also becomes a circulation. So whatever goes to the sink, that comes out from the source. Yeah, you can think like that. Or maybe you can look at this example. You had some capacities and have this flow. So there is integrality theorem for circulation as well. If capacities are integer, then it's a integral circulation actually. The circulation exists, but also you can uh, take integral value. So the maximum circulation can be integral value. So and if you have even if you have lower bound, that still holds. If capacities and lower bounds are integers, then there is a circulation. And that's also integral value. That's what shows our feasible matrix surrounding. So you can put those values that I have put earlier in the feasible solution. And then you can see at every edge the constraint can get satisfied. And this is how you can get. And finding this and finding, so as you have already seen and as we have discussed before, uh, yeah, if you have integral valued capacity or say lower bounds, we discussed only for capacities. Right? You can uh, keep each flow uh, at each step to be integral valued. So yeah, just from the same observation, uh, with the lower bounds as well, this will follow. So the algorithm is a bit different, but yeah, you can, after tweaking it, you can see that you can find a solution. So you can tell the computer to find such a solution. Now, if I come back to the image segmentation, I had I want to segment into foreground and background. What you do, so what is the procedure? I label each of the pixels and assign some likelihood values, non-negative likelihood values, and a penalty. If I by mistake assign more uh, likelihood value uh, for a background pixel to for foreground, then I'll assign a higher penalty. So at the so and what you want to do? We wanted a partition of the pixels a comma b. Now you can see why I wrote like this kind of a comma b. This basically will give you a cut so that this values becomes maximized. So whatever you have the foreground, whatever you have in the background, minus the penalty. You need to minimize the penalty and maximize this. Now, if you write in other way, so Can write it like this. The sum of the AIs over A will be the sum of the AIs over V minus over B. Same for BJs. And yeah, penalty remains the same. Now this thing is constant as it is all the vertices, all the pixels. This thing is constant. So maximizing this whole quantity, same as minus of this whatever, minimizing this quantity. So yeah, like this. Now we had our min cut problem, right? So we can solve like that, solve through that. So what we do, just formulate this min cut problem. I just introduce one source, one sink, and um, assign one directed edge to J. We take the value to be AJ and assign one directed edge from I to T and take the capacity to be BI. Okay. These are capacities I'm putting. And what about these two? Maybe for I and J thing. Yeah, this is basically bidirectional. So what I do basically put uh, anti-parallel edges and just put the values there, put the edges there. So and basically find the min cut solution that will give us the solution. So that's what I wanted to talk about. You can maybe try to write one algorithm. You can take a photo and try to write one algorithm, see if that works or not. Of course, you need to assign these values. This is the manual work that you need to do. Although through learning, then can say, or you can write some statistical algorithm. Maybe you can tune or try to consider these as parameters and to many different images, you tune to write one algorithm and you tune these parameters. So learning also you can try to do that. Although there is a better algorithm now. Maybe this is although this is uh, oof, although there are better. Yeah, in 2004 it's called grab cut. That you just select some portion. Maybe you have seen this in Google Photos. You select maybe 1 or 2 years ago. This was in Google Photos. Now, although they use their artificial intelligence model to just separate the background and foreground. So what it does basically select some portion of the image, so this part, and after that the algorithm uh, instantly separates the background and foreground, and this is very accurate actually. This is by the author Kolmogorov and Blake. 2004. I'm going to try to read up this. Although I'm not sure if it is accessible to high school students, but yeah, can try. Can anyway try. One thing is this Ford Fulkerson algorithm. If you take capacities to be infinity, it may not end it. Complexity is actually order of number of edges times the value of the flow. So whatever value of the flow is. Or maybe I should not say this. This is basically probably max cut. Never mind. Max cut. Complexity. Uh, so if there is a cut where one capacity is very high, then the time for focus will take will be very high. So it's not a very good algorithm, but there is a refined version by Dinitz, Edmond, and Karp. Although they actually based it on the Fulkerson algorithm, but it actually guarantees to time. Actually, they find uh, that augmented path, that shortest path through uh, um, breadth first search. If you have seen the breadth first search of the graph algorithm, and they actually redu- reduce the capacity like this order of number of vertices times the number of edges there. Now this actually registered for finite network, of course, talk about finite networks. It doesn't depend on the capacities, so only on the network. It should be fine. And you can find many more applications like in decision path, circuit design, early scheduling, or maybe project selection according to its. So that is basically yeah. So join V to W if V is prerequisite of W. If try to find a maximum matching there, you can try this, or maybe baseball limit. After a certain number of match happens, uh, you want to know that uh, which 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 of the matches will be waste of money. Say which of the teams won't qualify anyway. That you can find saying this network flow algorithm. Yeah, and yeah, this is one example that is very useful. That your liver and the hepatic, if the image of the liver and hepatic vascularization segmentation, that you can look it up. Yeah. So thank you. That's it for today, guys. Maybe I write some references. Uh, Maybe one is that algorithm design by Kleinberg and Tardosh. And to, yes, did not forget that should be one network flows, right? Theory application, theory algorithms and application. Theory algorithms and applications. So that is Ahuja, Maganti, and all. Okay. Yeah, these two are the references. Although you can find plenty of YouTube videos nowadays, plenty of notes, is because this is very well established area. So, any question? You can write it on the chat or mute himself.
Okay, thank you, Bikram, for the wonderful talk. Uh, now you guys can ask any questions that you have. Please feel free to.